No GPU, no engine, no graphics library. Lesson 3 drew shapes and never once asked what a number costs. Today we ask, and the answer is worse than you would guess. On this processor, a multiply takes about 130 clock cycles and a divide about 150. An addition takes 3. One divide is 50 additions. You could have drawn half a picture in the time. And before anyone files that under history, an ARM Cortex M0 has no divide instruction at all. Neither does the base RISC-V instruction set. Neither does an AVR. The chip in an Arduino. On an ESP 8266 there is no hardware divider either. Write a slash in C on any of those and the compiler quietly calls a subroutine. So this is not a lesson about an old machine being slow. It is a lesson about what you do when the arithmetic is expensive, and that is still a question with a paycheck attached to it. Volkov Commander as an editor. A new file math.asm. The usual head and 2 names we will want. The jump over the gap, same as last time. Everything that is not a frame goes in there. Everything that is not a frame goes in that gap, and the first things are the words we are going to put on the screen. They are just bytes with a 0 on the end, sitting in the program exactly like hello did in lesson 2. And the wait for a key, which you already know. And 1 to put a string on the screen. It walks the text a byte at a time until it meets the 0, and writes each character together with its color because a cell on the text screen is 2 bytes, and Stasor writes both at once. Now the machine. Mode 3 is the text screen 80 by 25, and setting the mode clears it for us. First the 2 captions, so the screen says what is showing. And here's the whole lesson in 4 lines. A cell on the text screen is 2 bytes the character, then its color, so we write a word and get both. 0E is the color, 05 is the character, 5 the number 5. And 24 cells to the right, the same thing again except this time the character is 53. And 1 line underneath, saying the thing out loud. Then the way out. These 4 lines stay the last 4 lines of the file all the way through. There they are, 2 bytes side by side, and they are not the same picture. The left one is a club, not a 5 a club, because in this font code 5 is a club. The right one is the digit, and its code is 53. So the number 5 and the character 5 are different bytes, and nothing on this machine will ever turn one into the other for you. Lesson 2 said the letters in hello were the bytes themselves, lying in the file in the order you typed them. This is that same fact from the other side, and it is the one beginners are never shown. If you have ever held Alt and typed a number on the keypad, that is exactly this. You are entering a code, not a number. Try Alt 5 and Alt 53 in any DOS box and you will get these 2 characters back. Which raises a question. If a number in a byte is not the characters that spell it, how does anything ever print 1? Badly is the answer. Up to the top, into the gap. Before a line of it, let us do it by hand because this is the part where people are usually shown code and left behind. Take 64,000 apart by dividing by 10. What falls off the end is the remainder, and that is the last digit. What is left is the quotient, and that is everything still to come. Then do it again. 5 divisions for 5 digits, and look at the order they came out in: 4, 6. Backwards, so they go onto the stack, and the stack hands them back the right way around. And then each digit has to become a character, which is one addition. 6 plus 48 is 54, and 54 is the code of the character 6. Now the code, and every line of it is one of those 5 lines above. Divide by 10. The remainder is the last digit. The quotient is everything still to come. div works on dx and ax together, so dx has to be cleared first or it divides by something enormous. The digits come out backward units first, so they go on the stack, and the stack hands them back in the right order. And here is where the byte becomes a character. Add 48. 48 is the code of the digit 0. And whoever laid out ASCII put the 10 digits in a row on purpose, so digit plus 0 lands exactly on the right character every time. And the words this next frame needs, plus 3 numbers to keep count with. And one small helper, because the next frame writes all over the screen. Give it a column and it works out where that cell is on the row we are on. Now use it, and not just to print an answer, because an answer proves nothing. We are going to make the program print its own working. $64,000, and the row of the screen we are writing on. Then one line of the screen per turn of the loop. First the number going in. And here's the division itself. One instruction, and it hands back 2 things at once: the quotient in ax and the remainder in dx. Print what is left over, and then the digit that fell off in white, because that is the one we are collecting. And round again, until there is nothing left to divide. Seven and 64,000. 5 digits, 5 divisions, and every divide on this machine is those 150 cycles. Printing a number is one of the most expensive things a program of. 10 is not a power of 2. That is the whole problem. If we wanted it in binary or in hex, we could shift and be done, but people count in tens, and the machine does not. So, no floating point and divisions we cannot afford. What can you actually build with that? Physics as it happens. 3 numbers at the top and a rectangle to draw with the same one from lesson 3. And the frame itself. A floor to land on. Now the numbers, and again by hand first, because 8.8 is a name for something very simple and the name helps nobody. A word is 16 bits. Read the top 8 as whole pixels and the bottom 8 as 256ths of one. One word, both halves. So 8 pixels down is 2048, not 8,2048, and a speed of 40 means it moves a sixth of a pixel each step, which is far too little to see, and after 10 steps it is moving a pixel and a half. Nothing in there is a fraction. 2048 is a whole number, 40 is a whole number, and the decimal point exists only in our heads. 100 steps, and every one of them draws without rubbing anything out. That is deliberate. We want the whole flight standing still at the end. And here is the whole of fixed point. To get the pixel, take the top byte. That is it. A shift of 8 is just reading the other half of the word. Sideways, the same 3 pixels every step, forever. Nothing accelerates it and nothing slows it down. Now the falling, and before a line of it, where is the mass? Because every physics lesson you have ever sat through had a mass in it, and there is not going to be one here. There is none, and that is not us cutting a corner. It is Galileo's. A heavy ball and a light one fall at the same rate, because the pull on a thing grows with its mass exactly as fast as its mass resists being moved. The two cancel out. Force equals mass times acceleration, so acceleration equals force divided by mass. And once you have done that division, the mass is gone. What is left has only 2 lines in it. Speed grows by the same amount every step. That is what acceleration is. Height changes by whatever the speed happens to be. 2 additions, and there is no third thing. And so you are not surprised in a minute. When the height reaches the floor, we are going to turn the speed around and keep 4/5 of it. That is the bounce, and losing the other fifth is why it dies down. the floor, and one number worth stopping on. 8.8 in a signed word runs out at 127 pixels, because 128 times 256 is 32,768, which is negative. You buy the fraction with range, and you have to know where the edge is. And the bounce, which is where the multiply finally earns its place. We want 4/5 of the speed back. 4/5 of 256 is 204.8, call it 205. Multiply by 205, then divide by 256, and you have multiplied by 4/5 using only whole numbers and only one real multiply. And there's the flight, all of it at once. Look at the gaps. Sideways they are all the same, because sideways nothing changes. Downwards they get bigger, and the steps took exactly the same time. Equal time, growing distance, that is acceleration, and you are looking at it rather than being told about it. Then it bounces and comes back lower, then lower again. Nothing in there knows the word energy, it just keeps 80% of the speed by multiplying and taking the top half of the answer. No floating point anywhere, no divide anywhere. One multiply for the bounce and one for the address, and everything else is adding. That is the trade this whole series runs on. Give up the decimal point, keep the fraction in the low byte, and arithmetic stays cheap enough to do 60,000 times a second. The sign table in the games is the same idea. The values are sign times 256 for exactly this reason. Next time we make that table with a program and find out that the one in the game has a number in it that is wrong. And when you go back to your microcontroller and see a slash in someone's C, you will now know what it costs there too. Next, a table of signs made by a program and a square that turns.